What is all this? This is all Chitango, sorry. Fine. So, I'm sorry for the previous live stream. There was some problem with the URL. So we come back to where we left off. So I'm assuming that most of you have already gone through my introductory video, which by mistake wasn't live. So anyways, here I am and here you are. A few of you, I'm sure. I'm Rohit and Nayan is there, and just want to shout out, hi Mukesh sir, if you're watching me. Namaskar. So in my last the previous webinar, I had talked about why is there a need for histograms, and so we'd seen very clearly that histograms tell us the frequency, the number of times every pixel value. So a picture is made out of different values. So every value, how many times is it occurring in an image? How many times is the gray value 1 coming in an image? How many times is the gray value 50 coming in an image? So the number of frequency, the number of times that a particular pixel value is occurring in an image, if you can diagrammatically show them, it is called a histogram. So this histogram can also tell you about the distribution, the probability distribution function, the uses of which we will see in the coming slides. So let me just confirm if it's working or not. So I think it is working. Nayan is saying, yeah, sir. And Rohit is saying, my internet connection is very slow. So I am having a feeling that for the live webinar, it's just Nayan, Rohit, and I don't know if Mukesh is watching, and myself. So anyways, something better than nothing. If you want to chat and if you've got some problems of what, you can either WhatsApp me or you can use that chat Chitango that's there below the web page, below the video. Yeah, I got a message. I could hear that message. So let me just see. There was a message from Chitango and says, hi sir, good morning. Oh, Mukesh sir is visible for the chat. See you. Good to see you, sir. Thanks for the support, because this is the first time we're having a webinar, and I really find myself like a mad person talking to myself or my family members telling me what the hell you're doing, speaking to yourself in a room. So anyways, hi Mukesh sir. Okay. So this was, so let's get back to what we're doing. So again, rebrushing. Today we're going to talk about a lot of enhancement. We're going to do enhancement in the spatial domain, not in the frequency domain. So in the spatial domain, you've got so many enhancement techniques. Intensity transformation, spatial filtering. So intensity transformation, all of these are normally done pixel wise. So this is point processing. Each pixel decides its own output. The spatial filtering is neighborhood processing. Unlike point processing, the neighborhood filtering depends upon a group of pixels together decide for the output of one pixel. So if I need to change, then my neighborhood decides my change. That's neighborhood processing. So neighborhood processing, a kind of neighborhood processing for enhancement is spatial filtering. So this is for the next part of our webinar. For this part, we're going to do point processing. So if I'm going to be enhanced, if I'm a pixel and I've got some value, and if I'm going to be enhanced, I'm responsible for my enhancement. So that is called point processing. So let's start off. Now we've seen what is an histogram. Then we've got to see what is a contrast in an image. We've already talked about contrast. This is a low contrast image and this is a high contrast image. If you look at the histogram of an image, like we talked about what is a histogram, you would see that the frequency distribution of this particular image will have a very narrow dynamic range. What do I mean by narrow dynamic range? I mean by this here. this particular frequency domain of this picture, this dynamic range is very narrow. So this picture has pixel values, only few pixel values. You know, if you plot it, it's this broad. It's a very narrow range. Whereas it could have taken up the whole range. So if your histogram is a narrow range, it has got low contrast. So even likewise, this contrast here, this image has very low contrast, and this image has high contrast. Now, what do I mean by contrast? I've got another image here. I just want to check if the messages are coming. Okay, it's not from us, it's from some other. So if you can see, our eyes have some biological restrictions because of the rods and cones and so many. I have given you an assignment in class. So if we are able to distinguish, researchers say that we can distinguish 30 odd gray levels. If it's a gray color, so our eyes can distinguish, we can separate 30 different shades of gray at one time, and not more than that. So that's the limitation of the eye. Whereas if you've got 8 bits to represent 1 pixel, you can have 256 shades of gray. So our eyes can distinguish 30 at one time, but you have the capacity to have 256 shades of gray. Yeah? So if you're going to use grays that are very close to each other, like this black, this gray, this light gray. So if you're going to have an image with only these 3 values, then it is going to have a very low contrast, something like this image. But if you're going to use gray levels of varying degrees from white to black, all of these grays, then we say that image has a very good contrast and eyes can distinguish between different shades and shapes. And this is an image that has a very high contrast. Okay, so that is contrast. So then if you can plot this, the number of times this black pixel is, how many black pixels are there in this image, how many light gray pixels are there in this image, that graphical representation is called the histogram. So it says here, it also says here, please refer to notes or the web page. So I've got a web page to make you understand this. So I've got this tutorial point to solidify the answer. So here you can see same case here is, if you have a look at these 2 images now, and he talks about brightness. So what is the difference between contrast and brightness? It's a very subtle difference, but pay attention. Brightness is an overall increase or decrease of pixels. So if you've got 5 pixels, if all the 5 pixel values are 1, 1, 1, 1, 1, all these 5 pixels have a pixel value of 1. And if you increase this pixel values by 5, all of them, so instead of 1, now you got 5, 5, 5, 5, 5. Or if you increase by 5, 6, 6, 6, 6, 6. So what have you done? You've increased the brightness of this image. So if you increase all of the pixel values together or decrease them together, you have the brightness effect. Is the picture dark or is it bright? And if you plot the histogram, most of the pixel values, if they concentrate towards the left side, was dark. We've seen in the previous class. Yeah. If all of the pixel values have their pixel intensities towards this is the whole scale. And if from the half point, if they go all to the left side, it is a dark image. And if all the pixel values are concentrated to the right side, it is a bright image. So similarly, if so that is the brightness value. So brightness. So if you have so this guy, he's taken this image. Now this image is made up of 5 rows and 5 columns, something like this. 1, 2, 3, 4, 5 rows and 5 columns. Now this picture is, it seems black. Why? Because all of the pixel values are 0. All of the pixel values are 0. And now it's not that 0 is colored black. It's just that we've spread the gray color on top of we've spread a black color on top of the value. So 0 means black, 255 means white. It would have been a green color, like I said in my previous class. Or it would have been a red color. So if 0 means red and 255 means white. If it is a blue, 0 means blue and 255 would be white. So but here we're talking grayscale, so it's a black color. So this image is 5 rows, 5 columns, and all of them are black. Now if you take 2 similar images, image 1 and image 2, both of them have 5 rows and 5 columns. This has 5 rows and 5 columns. Now we're going to change this. We're trying to change the values of this image 1, and we're going to compare it with image 2. So we increase all the pixel values of image 1 by 1. So you increase a 1, so all of them were 0, all of them were 0. Image 2, all pixel values were 0. Image 1, all pixel values were 0. Now, image 1, we increased all of the pixel values from 0 to 1. 1, 1, 1, 1, 1, 1, 1. And then we compare them. When we compare them, this is your image 1 and this is your image 2. You don't see much difference. Then again, you keep iterating and then you increase the image 1, this pixel, not by 1 now, but we do so by adding 50. So now this becomes 51, 51, 51, 51. All of these pixel values, once you add 50, it becomes 51, 51, 51, 51. All of these image 2 pixels are 0, 0, 0, 0. So when you compare this, now when you increase by 51, you see a slight change. What's the change? We see that the image has become brighter. When you compare it with image 2, you can see the image 1 has become brighter than image 2. Why? Because image 2, all of the pixel values are still 0. And whereas the image 1, after repetitive iterations from 0, we've increased it, in various increments, and it has become 51, 51, 51, 51. So if you increase it further by 45, so if you add 51 to 45, and the image very prominently looks very different. This is very bright, not very bright, compared to 2 it is very bright, and 2 still remains dark. Now so this is brightness. Now what then is contrast? So I'm referring to this individual image, this image 1. Image 1 is bright image as compared to image 2. Fine. But if I take both of this image together, then I would say there is a very high contrast. But if I take only this image, there is no contrast, because all of the values in this image are the same numbers, 1, 1, 1, 1 or 5, 5, 5, 5, 5. There is no difference. There is no ratio between maximum minimum. Here there is 0 contrast, dark image. This is 0 contrast, bright image. Because, for example, again, he's taken this image where all of these pixel values are 100. Fine. Now contrast is the maximum. So the maximum value in this image is also 100. The minimum value is also 100. So contrast is the ratio. If you can subtract the minimum from the maximum, and then that would be the contrast. What is the difference between different colors? If one color is light gray, the other is black, you can distinguish the colors very nicely. Okay, so Rohit is also saying hello, sir. I think he joined in late. Anyways, Rohit, hello. You can rewind the video and see this later on. But so we were going back here. Sorry. So we were here. Now, so the contrast means what? The brightness is, the previous image had all zeros. So that was dark image. Now this image is all 100. So this is a brighter image compared to the previous one. But what is the contrast? What is the difference between the pixels? All the pixels are very similar. So when there is so much similarity, that means there is 0 contrast. When there is a lot of dissimilarity and you can distinguish one object from the other, when you have photographs, you need to distinguish a tree from a building. You need to distinguish a lamppost from a signboard, especially when you have imagery from the satellites around 800, 850 kilometers above the ground, above the clouds. The satellites are taking images. Now you need to distinguish between different objects on the ground. So if the contrast is very low, all of the colors are almost similar, then the visual interpretation is going to be very difficult. It's very difficult to visually identify different objects. But if the images are going to have very different valued numbers and very different colors, and the contrast is going to be high. So the difference in maximum minimum. So in this image, the maximum is 100, minimum is 100. If you see, the contrast is 0. So even though the brightness is there, there is almost no contrast. Okay. So that was about the contrast, and there is one particular slide I wanted to show you. I don't know why my PC has become pretty slow. Histogram introduction. Yeah, so I've already done histogram, but anyways, histograms are not only used for images, they can also be used for many other scientific statistical studies. For example, this is a histogram for the number of people that are interested in subject. So for Java, the number of people interested is around 4.25. So the frequency of people interested in Java is quite high. You can see Python is pretty low. C# is also okay, and C++ is the highest. So that is the popularity histogram. You can even take midpoints. You can take this midpoint, take this midpoint, this midpoint, this midpoint, and you can draw a very smooth curve over this, and then you would see density histogram, like the ones we saw of the image. And we see here again there is two modes. One is one mode, there's a highest point, one highest point, and two highest points. So again we can see that very clearly that this distribution, this data distribution for this particular data is multimodal. There's one mode up and there's another two mode. So whenever you process images, one very important feature to keep in mind is the mode of an image. Does it have only one mode? Is it normally distributed? Normally distributed means, does it have a Gaussian distribution, which I'm going to talk about maybe in this lecture or maybe in the next lecture. So if it has a normal distribution, what are the processings that must be done? If it has more than one modes, which means multimodal, what are the processing that must be done? What must you keep in mind? So all of these things are there. So apart that, even grades, you can have a grades histogram, who the number of students, the frequency of students, the number of students who've got A, number of students who've got A minus. So all of these are, you can see if you draw this density graph, if you touch all of this, you'd have a curve from here, it comes straight, and then suddenly it increases. So this is called a negatively skewed, a positively skewed. Skewed means it is highest here, and it is lowest there. It has a tail. So there are characteristics of histograms which we must be well versed with if you want to be very good in image processing. Okay, so that's another thing. So likewise, he's got this Albert Einstein Guruji ko photo here, and Guruji ko histogram dekhiye bhane, you can see this is a very good image. You can see here, if you draw a graph here, density graph, you can have a nice curve, just almost a curve. Almost the curve is almost in the center. So you can have one line going one hill. It only has one hill. So we can say this photograph is almost a single mode image. It's one of the simplest kinds of image, and most of the methods and most of the studies assume that it is a normal distributed study. So this is what we mean a normal distribution, almost a normal Gaussian or almost Gaussian distribution, one mode, and it is only the highest point is almost at the center. It may not be at the center, but it's almost at the center. And other thing you can see is that it has a very good contrast. Yeah, it is a single mode. It is only one peak. The peak is it's not entirely to the left, it is not entirely to the right, it is almost to the center. So you can say it is a very normal distributed single mode histogram. And the other thing that you can, when you analyze these histograms as an analyst, is that the range of values that this image has. This image has pixel values 0. It also has 50. It also has 100. A lot of 150 pixels. There's a lot of 150, 200, and it has 250, 255. So the range of values in this pixel is from 0 to 250, all of the values. So the dynamic range, that's what we call the dynamic range. The dynamic range of this image is almost the whole 0 to 255 available. So that means it is a very good contrast image. Okay, so we've analyzed the histogram. And from the histogram, what have we analyzed? We've seen that this is a single mode, only one hill, almost a single hole. So single mode histograms that have the mean almost at the center. This is not exactly at the center, but almost at the center. It's called a normal distribution. It's also called a Gaussian distribution. This is almost semi-Gaussian distribution. Sometimes the center can be all the way to the right. So if this is all the way to the right, we'd say it's a very dark image. If the center hill, this like a camel hill, if this hill is all the way to, if the hill is somewhere here on top here or towards the right, then we'd say it's a very bright image. Bright values are a lot there, and image will be very difficult to see. If this hill was towards the left, it would be a dark image and very difficult to see. But somewhere it's in the middle, and then it's got a mean and median, standard deviations are there, and this is a single mode, and since this is well distributed, we know it is high contrast. Fine. So that sums up the basics for our class. Now we know what is a histogram, what is it used for, what do you mean by contrast, which images have low contrast, which images have high contrast. How can you know that an image is dark? By looking at histogram, because all of the histogram values will concentrate towards the left. How do you know that an image is bright? Looking at the histogram, all of the frequency distribution of the histogram, if it concentrates towards the right, 255 towards 255, then you'd say it is a very bright image. How do you know that an image has a very good contrast? If the pixel values or the histogram, if you're looking at the histogram of an image, if the histogram takes up the entire range of the dynamic, it uses up the whole dynamic range, 0 to 255, then you've got very good contrast. When do you know it has, when do you know that an image has very low contrast? When the values of the pixel, or when if you're talking in terms of the histogram of an image, when the histogram values of the image take up only a narrow band of the dynamic range, it doesn't take up the whole dynamic range, it takes up only the narrow band of the dynamic range, then we can clearly state that that particular image is low in contrast. Okay, so in the spatial domain, one kind of enhancement is called the contrast stretching. So we already know what we mean by contrast, and stretch means, so if you've got kind of a rubber band, you've got this rubber band, if you can take the one end point and stretch it, and you take another end point and stretch it, so if you can stretch both the end points, that's called stretching. So if you've got a contrast has a minimum value and contrast has a maximum value. If you can stretch both these endpoints and all the in between points get stretched to take up more space, that's called stretching. So as you can see, the logic of this contrast stretching can be shown through this transformation diagram. Now on the x-axis is your R. So R means point processing, we've already talked about. So pixel by pixel, spatial domain, not frequency domain. And towards the y-axis is your output image. The input image is the x-axis R, the output image is the S. This is pixel by pixel value. R is the input pixel, S is the output pixel. This, we are talking pixels, so that's why there is no G of xy, T, F of xy, it is S and R. Now, contrast stretching means there is a certain value M, and below that all values in the input image below M, so they go 0, 1, 2, 3, 4, whatever, to some value M is compressed. You can see. So what is the value of, if the image value is 10, say 10 is somewhere around here approximately. So if it is 10, what is the output? Output is 0. So 10, 20, 30, 40, probably 50. So when the input image value is 50, the pixel value is 50, what is the output? It is still 0. Then 50, then 60, 60 probably will be this point here. 60, if you trace this up, and if you go to the output, so when the input value is 60, the output is almost 10. So you can see, so all pixel values below a certain number, certain number, M is compressed to darker regions. That's what we can see. And all values above M in the input region are expanded towards the brighter region. You can see here. So for example, I'll take this point here. Okay. So just the point just a little bit right of this M. From the midpoint, I take it somewhere here. So if this whole range is 0 to 255 here, so this mid range will be around 110. So if I'm taking a value of 120 or say 140, I take a value of 140. So this is 140. So input image is from 0 to 255, any value, and output is again obviously 0 to 255. It's mapped. So if I'm taking a value of input value, for every pixel value whose input pixel gray level is 140, what will be the output? You draw a line straight away, it goes straight here. What's the output? 255. So for 160 input value, you are mapping it to 255. So all values above M are expanded or increased towards the brightness, towards the brighter scales, and all values below M are compressed towards the darker scale. So that is what is mentioned here, darkening the levels below M in the original image and brightening the levels above M in the original image. So this is what we mean by contrast stretching. We are stretching it. The brighter values are becoming brighter, like the rubber band example. The minimum or the maximum values are going towards maximum 255, the minimum values in that image, whatever may it be, 10, 15, 20, it's being stretched towards the minimum of the output, 0. So, and all the in between values are arranged accordingly. So there are many examples of contrast stretching. There is a minimum, maximum, linear contrast stretching, percentage. So this contrast stretching again can be linear and non-linear, like we saw in our previous example. So contrast stretching linear family means when the input increases, the output also increases. When the input decreases, the output also decreases. So there is a linear relationship, some kind of a some kind of a straight line. When you map it, you have almost a straight line between an input and output. There is a linear relationship between input and output. So contrast stretching methods that show these linear behaviors are min-max, linear contrast stretching, percentage, linear contrast stretching method, standard deviation, linear contrast stretching method, and piecewise linear contrast stretching method. So these are all the linear contrast stretching methods. So apart the contrast stretching, so contrast stretching is one. No, there's a linear methods. So contrast stretching, non-linear methods also there. So what are the non-linear methods? We've already seen some in the class called histogram. Not histogram, sorry. Log transformations, gamma transformations. We talked about image negative. So all of these things are there. Histogram processing is another non-linear contrast stretching. So in image enhancement in the spatial domain is contrast stretching. Then you've got image negative. Then you've got thresholding. Now, what is thresholding? Thresholding is again similar, a very basic image enhancement techniques where the output of a threshold image is again binary, something like an image negative. If you remember to image negative, for every pixel we deducted 255 or L-1 from every pixel, and image negative, white became black and black became white. Here every image will be turned into binary, one of the two colors. So it is here. So it's again explained as G of XY. So this is not a point processing, this is an image processing. It's a neighborhood processing. So G of XY is the output, and so the function is defined as such. So when does G become 0? G becomes 0 when the input image is less than 127, and G becomes a 1 when the input image f of xy is greater than 127. This is the logic is represented here in the transformation diagram. So this is x is the input image, this y is the output image, pixel values. So m is for our case in this example is 127. This is only an example. 127 can be any value. So this is a threshold. This is called thresholding. So there's certain threshold. The threshold is m. Yeah. So this m can be 127 or whatever it may be. So if any value below m is mapped to 0. So all pixel values in the input f of xy. So this is f of xy. All pixel values 1, 2, 3, 4, 5, 6, 7, 8 up to m. All pixel values. When you do this transformation, what happens to the output image? All the values become 0. If the input image has 1, output is 0. If the image is 10, output is 0. If the image is m, it is still 0. But what happens if it is m plus 1? When it increases, when it's greater than 127, if your m is 127, then it straight away gets mapped to 255. So all input images above m plus 1, m plus 2, m plus 3, m plus 4, m plus 5 till 255 or L minus 1. So all of these images, input images will be mapped to 255 in the output image. So you'll have either a black and white images. So this is an example where we've seen already done in the class a log transformation. In a log transformation, we can see a narrow band of input images. So all of these input images are compressed, and output, the brighter images are expanded. So negative means it changes the whole image. Identity means it keeps the same. So this is not the class. This is not what we're going to do today. So you see all these are image negative. Here, this is image negative. So we've seen image negative. Here you go. Image negative. So for every input 0, the output is 255. So if the input is 255, the output becomes 0. So white becomes black, black. It is an inverse. So the use of negative images, here you go. This is a photo of some mammogram for some medical imaging. So a mammogram, and there seems to be some disease. Now he wants to see what disease it is. He wants to be clear of the spread, or the ulcer, or whatever it is. Now when you take the negative of this image, and suddenly you can see this image a lot clearer now. And so it has many uses in the medical system. So this is only about the log transformation. Fine. So there are a lot of okay. So now you go back to your notes. And you can see I have explained what is a contrast. Yeah, what is a contrast? Now we've already seen what a contrast is. Here you go. This image has very low contrast because the histogram shows a very narrow band, and there is a lot of difference between interpixel differences here. Very less interpixel differences here. There's a lot of interpixel differences. Then what is contrast stretching here? When narrow bands are stretched towards the dark and brighters are stretched towards the brighter parts, that's called contrast enhancement. And then what is linear contrast enhancement? If they are linearly mapped. So this is the input. This is a histogram of the input image. You can see. Yeah. So this is the minimum is 84 and maximum is 153. So maximum in pixel value in that image is 153, and the minimum pixel value of that image is 84. Now this 84 is somehow stretched to 0 and corresponding simultaneously with the same proportion all intermediate images pixel values are mapped, and the maximum value 153 of the original image is mapped to 255 of the output image. So now this image that previously had values ranging from 84 to 153 has suddenly taken up values from 0 to 255, which has been linearly stretched. What has been stretched? The contrast. So the image is has better visibility. So let me see I got another message. Okay. Now here you go. So what are the most common linearly stretched methods? There are minimum, maximum, percentage, and piecewise. That's what we're going to see in the next class now. Again, I've got another image here. Look at this image. This is a thermal image. Thermal image from the satellite. Previously, we'd seen camera photographs, digital camera photograph. This is a satellite photograph of an area called Charleston, and it is a photograph taken by a satellite called the Landsat satellite, and it is the image number is 4. So a satellite called Landsat has taken an image. The number of the image, the numbering of the image is 4, and this image, the satellite image, is taken from way 800-900 kilometers above sea levels over an area called Charleston. Now when you see the frequency or histogram, when you plot the histogram of this image of the Charleston, then you will see that this is the histogram. Now from what we've studied, what can we see, what can we infer from this histogram is how much modes is there. So let's say how much peaks are there. So 1 peak, 2 peak, and 3 peaks. So there are 3 modes. So we say that this image is multimodal in nature. This histogram is multimodal. It's not a single mode. So you cannot mistake this as a Gaussian distribution. What else can we observe? We observe that most of these, the histogram values, the frequency value, most of these pixel values are concentrated towards the left side of the of this entire dynamic range. So the pixel can be of any value from 0 to 255. The midway is 128. These are the brightness values. But the image pixels have chosen to concentrate all towards the 0 side. So which we can say very intuitively that whatever image we've clicked, looking at the histogram, it must be a very dark image. And since it has 3 modes, which means it has 3 different objects or 3 different colors in that image. So let's see what are the 3 different colors. So there is all these black parts. You can see all these black parts. Maybe this is a river, sea, whatever it may be. So all these black parts will contribute to this long frequency stretch in this histogram. Then there are other lighter parts that would resemble this, and there are whiter parts here, a little whiter shades all over here, whiter shades. So this is the third mode. So there are three objects. We cannot know which is which. Obviously, we cannot, by looking at histogram, we don't know what objects are there, but we know there are three objects or three distinct colors. We know that this image is dark because all of the frequency values, all of the brightness values are concentrated towards the left. And we also know that since it not only is concentrated towards the left, all of the minimum and maximum values are, the difference between the minimum and the maximum value is very small, because it could have taken up any of these values. So the contrast is also very low. So we can enhance this image. Because you cannot just perform enhancement on any image. We must first know that an image needs enhancement, and we don't want to land up with the wrong enhancement. And so now we know this image needs an enhancement, this imagery needs an enhancement. So once we're going to do a contrast linear stretch. So one of the first methods of contrast linear contrast stretch is the maximum minimum linear contrast stretch. Once you apply the maximum minimum linear contrast stretch on this image, on this previous image, then you can see that there is a very stark difference. Suddenly the image looks brighter, and you tend to and visualize, interpret. You can see objects. You can, if you have some information about the ground truth, if you know this Charleston area well, then you'll be able to figure out certain things. And when you look at the histogram of the contrast, enhanced image, then compare it with the original image histogram here, and compare it with the enhanced image, and suddenly you see the image still has 0 to 255 brightness values, and the frequency is still there, 1000 pixels, 1000 frequency values, but the brightness values in this enhanced image have suddenly spread, and it's taken up the entire range of dynamic values from 0 to L minus 1. So for us 0 is 0, L minus 1 is 255. So it's an 8-bit grayscale image. So it has taken up the whole range, which means there has been a drastic improvement in the contrast of an image, and it has shifted its entire center from entirely being on the left to almost towards the center. So the brightness also has somehow increased. And then we'll see another similar linear contrast stretching method is the standard deviation or the percentage method. Now the percentage method is yielding an even brighter image because we can see that it has used up almost all of this values, and but we can see there is a lot of loss in information, because even though they have stretched this contrast of this image, and it looks really like high contrast, there's black and there's again white, there's black and there's white, so there's so much contrast, but in doing so we seem to have lost a lot of information. You can see this area, small areas near the white part, and here white part, everything has become white. So now it is difficult to distinguish what is what. There could be very important information here in this region, but when we did a one standard deviation, we see that all of them has become 255. So all of this area here, which had some information, have all been mapped to 255. So there is some kind of loss of information in standard deviation. So that is what the takeaway is. Contrast stretching methods, the maximum minimum linear contrast stretch does improve and enhance the image. The standard deviation provides even higher contrast, but with certain loss in information. Okay, so this is the same explanation in the notes that I have given, and somehow there is there seems to be something is missing. Anyways, seem to have lost something. Okay, yeah, this is it. Yeah, good. This is what I wanted to pick up. Okay, anyways. So now the first of okay, I need you to Rohit, at least if you can message me, and if you're still there and if things are really clear, I really don't know. So if you can just WhatsApp me, yes sir, or something, or Nayan or anybody, you can just WhatsApp me so that I know I'm still live. Okay, so when you do that, I'll be waiting for that. Maximum minimum contrast stretch. So next method is the maximum. So first method is the maximum minimum contrast stretch. What happens in this method? So most of these linear contrast stretching methods are best done when when you have a very normal distribution of histogram, something like this. Yeah. So there's only one mode, but most of the images don't have one mode because you're going to have lots of objects in an image. So even then you can use linear contrast stretch methods, but they are best fit for those images that have a single mode normal distributed Gaussian histograms. So in a maximum minimum contrast stretch, what we do is we've got an equation here. We've got an equation here that says BV out. BV out is brightness value. So this is output. So for every pixel output, what do? For that, but you're going to enhance every pixel one at a time. So this is point processing. So whichever pixel you're at, ij, so that particular pixel value, brightness value of that particular pixel minus the minimum value in the histogram. So that image has a minimum value. So that minimum value minus the current value, and that image will also have a maximum value. So the maximum value minus the minimum value. So min k is the minimum value of the image, max k is the maximum value of the image, BV in is the brightness value of that image, the current pixel that you are processing, and BV out is the corresponding output value. And okay, so good. So I'm getting at least some response from Nayan. Okay, fine. Rohit so gaya kya? He's written, sir, my internet is giving problems. So anyways, so what is quant k? Quant k is the dynamic range. So hamro 8-bit image ma quant k bhaneko, what is the maximum you can go? 0 to 255. So this quant k resembles 255. So BV in brightness value of the current image minus the minimum value of that image divided by maximum value of that image minus the minimum value of the image into quant k is the dynamic range. So as 0 dekhi 255 or 256 fine. So 255 is the quant k. So for every pixel you're going to map like this. So let's first, so here you go. BVN is the original input brightness, whatever brightness values are there in the image, pixel by pixel. Quant k is the total range, maybe of the display or of the image, is 255. Minimum is the minimum value of that image, maximum is the maximum value in that image. How can you find out quant k, minimum and maximum of an image? So because in order to do minimum maximum, if you're going to write a program, and in that program, C program, Python program, you're gonna plug in this formula. So how are you going to find out min, max and quant? Obviously we've already seen that you take an image, see the histogram of an image, and when you see the histogram of an image, you'll see the quant k, where does the scale range to. We've seen a scale range to, where does the scale range to? So okay, anyways, so where does the scale range to? You've seen here. So if you take an histogram of an image, then we see, here you go. Or better still, let's go a little above. Okay, so if you see an histogram of an image, if this is an histogram of an image, we'll see what is the range. Okay, the quant k is 0 to 255. So the quant k is 255. What is the minimum value? Here you go. So you just read the scale 0 to, if you can read the minute scale, it's 84. So min k is 84. What is maximum k? Is 153 and quant k is 251. So for every input image, say you're doing an image here, so the value of the input image is 50. So what is the output of this 50? How can you map this? If you change this input image and then you want to enhance it to make it an output, a better contrast image, so the 50 you'll have to do some calculation with this 50, BVIN. So this 50 is BVIN, brightness value at 50. So 50 minus what? Maximum 153. Divide by maximum 153 minus minimum 84 whole into the quant case 255. So that is the formulae for so these are the linear transformations we're going to see: maximum, minimum, contrast, stretch, which we are currently seeing. Yeah, so here you go, this is the formula. So 50 minus 84 and 180 and blah blah, whatever that is. Okay, so this is the way we perform. So the derivation of all of this is something I couldn't type it in the notes, and all of those symbols and integration and summation. So that is something I intend on doing once we get back to class. We'll derive equations, but till then you can write down these notes. You can see these videos again and again, and you can picture what is happening. The important thing is the picture, is not to mug up and write what is happening. See images, see enhanced images, see raw images. Now so let's see the logic of the just once. Hold on. Okay, it's supposed to come here. Okay, so somehow this image is a very important image. So I'm just gonna take this, I'm gonna control X, and I'm gonna put this back here. Here you go. Okay, so we've seen the formula, the equation for minimum, maximum, contrast stretch. Now let's see the logic of the contrast stretch diagrammatically. So if you see, for example, we've got, this is what I mean by a single mode normal distribution or Gaussian distribution. The mean is at the center, and there is no skew. Skew means all of these values are not concentrated towards the left, which means the dark image. All of these values are not concentrated towards the right, which means it's a very bright image. It is somewhere in the center. Now in this normal distribution, you can see this is the distribution of an image. Okay, now let me just set this up for you. Yeah, okay, now we can see the dynamic range for the display is from 0 to 255. So we know it's a 8-bit image. Each pixel is having 8 bits representations, and this particular image histogram has a minimum of 4 and a maximum of 104. Now if you were to apply a min-max contrast stretch to this image, so this is a min-max contrast stretch. Okay, so this is diagrammatically represented the logic of min-max contrast stretch. So if you were to apply a min-max contrast stretch, this is the output you get. So let's have a look at the output. Suddenly you see these tails, the 4 has been stretched. The 4 has been stretched to 0, and 104 has been stretched to 255. So it's also called contrast stretching. So somehow you stretch the two endpoints, and all the in-between values of the input image have taken up proportionally the output values in proportion to the input values. So all of these have proportionally set in their respective places based on the stretch, where 0 has become 4 and 104 has become 255. Now how do you interpret this? You can see the 4, the minimum of 4. So if the input image so if the input image has any value between 0 and 4, 0, 1, 2, 3, 4, the input image, if it has any value from 0 and 4 brightness values, it is mapped as 0 in the output. Okay, and so the 4 is almost pulled to 0. So all values that is above 104 to 255 is pulled to 255. So it somehow got a stretch, and only so this image only had values between 4 and 104. So 4 and 104 was linearly stretched. You can see this is a very linear line. So for every value input, you can map an output. For every input value, you can map an output. So this 4 was shifted to 0 and 104 was shifted to 255. So this is a very good diagram that explains minimum maximum contrast stretch. Yeah. So these are all there in the handouts that I've made for you yesterday. So please have a look at it. make notes. Okay, now similarly, let's take an example. Okay, so for the min max example, I've taken the trouble of giving you an example here. So we know this image, the image we have has a minimum value of 4 and a maximum of 104. So let's take the first value. So let's do this transformation. So first value BVI in. So brightness value of the first pixel is 4. So how do you do? If you plug in the formula above, so 4 minus the minimum in that image is 4, maximum pixel value in that image is 105, again minimum is 4 into quant k is 255. So if you do this calculation, it comes out to 0. So if the input image is of pixel 4, the output value will be 0. Okay, and let's take the last pixel of this image. The last pixel of this image is, what's the highest pixel is? 104 of the pixel. That's the last pixel value. So when you're plotting 104 minus the minimum of the pixel, maximum minus quant, again you get 255. So the first pixel is plotted to 0. The first pixel was 4, now it plots to 0. Then the last pixel, the maximum pixel brightness, the maximum brightness in the image is 105. Now it gets plotted to 255. And what happens to all the in-between values? All other original brightness values between 5 and 104 are linearly distributed between 0 and 255. So we've been able to stretch the entire contrast of that image. Then we've got the next method called the percentage or the standard deviation contrast stretch. Now it is similar to maximum minimum linear stretch. So the second example is percentage linear stretch. It's similar to maximum minimum linear stretch, but instead of giving the value of minimum and maximum, the value of minimum maximum here is a pixel value. So instead of giving a pixel value, if you can give an area percentage, 16% from the minimum or 16% from the maximum. So if you can give the percentage of pixels, all these percentage of pixels calculated from the mean. So the mean is the center, mean is the arithmetic mean. All of the pixel values are added, divided by the number of pixels. So the arithmetic mean. So the area from the arithmetic mean, if you give the min and max, instead of pixel values, if you give the area, then that's called percentage. If you give percentage of pixels from the mean, then that will be a percentage linear contrast stretch. Now if the percentage that you give coincides with standard deviation. Now what is the standard deviation? These are all univariate statistical descriptions. That is very important for images. So please go through univariate statistical descriptions. Please write it down. Univariate statistical descriptions for images. So, or the other way you can see it is image assessment using univariate statistical descriptions. So what does it mean? So I'm trying to assess an image. So I'm trying to look and analyze, and I'm going to talk about an image, and based on what? Based on I forgot what I was saying. Based on univariate statistical description. So what are the univariate statistical descriptions? This mode I talked about is a univariate statistical description. The mean I talked about is a statistical description. Now there is some concept about standard deviation and variance. So for that, I wouldn't want to mishmash this webinar with those terms and terminologies, but please make it an assignment that image assessment using univariate statistical description. Percentage stretch allows you to trim extreme values. Okay, so when you have a percentage stretch, so when you give a percentage of pixels from the mean, say example you had an image that ranges from 164 to 1908. So this is a pretty big image. It must be a 12-bit image, not an 8-bit image. So the minimum gray brightness values of that image was 164 and the maximum was 1908. Now if we selected 2% linear stretch in this percentage contrast stretching, then the lowest 2%, so 2% from 164 is the minimum, 198 is the maximum. So 2% of pixels from 164 towards the right and 2% pixels from from 1980 towards the left of the histogram values are less than 1 are set to 0. So the lowest 2% of the histogram values are less than 179. So if you come from 164, if you come 2% up, then you come to a value of 179. So 179 will become 0, not 164. 164 will not become 0. 79 becomes a 0. And if you come 2% below 198, you get 698. So 698 is set to 255, not 1908. So if you can see, and all values between, so 64 becomes 179, and then 179 is stretched to a 0, and the maximum value 1908 becomes 698, and this value is stretched to 255, right? So why so then if this percentage coincides with standard deviation, what does that mean? So I need another class for this, but in very short, for every image there is one standard deviation. So all images have a mean, the center. So if it's normal distribution is the center. So what do I mean by one standard deviation? So one standard deviation to the left, one standard deviation to the right. The area that covers that is covered by this standard deviation in that curve you had, we had this curve. So the area that is covered by the standard deviation would contain 68% of the values. Here you go. So 68%. So if you're picking data, so all the pixel values are there in the image. So 68% of all the pixel values, where do they lie? They lie within one standard deviation. If you go 2 standard deviation further from the mean, almost all of the data, 95% of the data, you'll find it there. And if you go 3 standard deviations away from the mean, you'd find almost 100% of the pixels within that area. So now let's see an example. Now let's apply a 1 standard deviation contrast stretch to the same Charleston SC image in file 3. Okay. Now here we would result a minimum case. So the Charleston image has a minimum of 12 and a maximum of 43. All values in between 12 and 43 are linearly contrast stretched to lie between value 0 and 255. All values between 0 and 11 are now 0. Fine. So let's see the Charleston image in figure 3. Here you go. So you've applied a 1 standard deviation to the Charleston image, and we've got some loss of information here. Like previously I said, why is there a loss of information? Why is there a loss of information? 1%. So we're applying only 1% contrast stretch. So why is there a loss of information? Here you go. So if you see this, previously in the maximum contrast stretch, what happened? The minimum value was stretched to 4 and maximum was stretched to 255. But here we must specify not the default min k and max k. We must specify how much standard deviation contrast stretch you would apply. So if we had, for example, if we say we want to apply 1 standard deviation contrast stretch, so for this particular image, 1 standard deviation is, the value comes up to 12, and 1 standard deviation towards the right positive side comes up to 43. So all values between less than 12, so there are some values after 12 and there are some values after 43, but all of them are lost because 12 gets stretched to 0 and 43 gets stretched to 255, and all in between values get linearly stretched over the 0 to 255 dynamic range. So that means what happens to the value 0 to 12? From all values from 0 to 12, the information is lost. They all map to 0. What happens to the value from 43 to 255? All of them are lost. They are mapped to 255. So hence we got a Charleston stretch here. We got a Charleston stretch here. So this was the real image. The first A image was a real image, which is very bad contrast. Then we applied a minimum maximum contrast the histogram frequency brightness values was expanded over more, the dynamic range became broader. And when you add one standard deviation, you got a maximum stretch, but you've lost certain information. So this is the values that we've lost, 0 to 12, and what was that? So there was some information lost. So this is why is there some information lost? So there's some information lost because of, yeah, also this one standard deviation for this image must, there's a calculation, there's a formula to calculate standard deviation. So when you say one standard deviation, it comes up to 12 on the left side, and here 43. So all values from 0 to 12 is mapped to 0. So 0 to 12, all values are lost. There are some information here. From minimum k to 12, there is some information that's lost. These are mapped to 0. There is some information from 43 to maximum k. Those are lost. So that is your percentage and minimum maximum contrast stretch. Okay. Then the final of the linear contrast stretch is called piecewise linear contrast stretch. Now, piecewise contrast stretch again is a contrast stretch where you can specify which part of an image you want to brighten, which part you want to darken, which part you want to stretch, and which part you don't want to stretch. So basically saying all the previous contrast stretches, when you applied it, it happened to the entire image. But it may so happen that you've got a particular image and you only want to make certain part of that image clear, and certain part of the image you can leave it as it is, or you can want to darken it or brighten it. So but you want to have a mixed model of contrast stretch. So that is that in that case you apply a piecewise linear contrast stretch, where piecewise means a lot of pieces. So a lot of linear 1, 2, 3, 4, lots of linear contrast stretches, all of them together we combine it and make it a piecewise linear contrast stretch, as shown in figure 5 below. So let's see the figure 5 below. Here you go. So if you were to logically represent the piecewise contrast stretch, this is what it looks like. You can see there are two control points here. This is point 1 and this is point 2. Right? There are two control points. So based on this, so you can move this point down, up, left, right. Even you can move this point down, left, up, right. So you can play around with these points, and when you play around these points, the image will have different intensity enhancements in different areas. Okay. So this piecewise linear contrast stretch, it takes up two special cases. Okay. The first case is when okay, so it takes up two special cases. One is when S1 equals to R1. So S1 equals to R1. So S1 equals to R1 means this value drops down to the 0. And S2 equals to R2. So this point is now here, and this point goes up here. Okay, so in that case, oh no, S1 equals to R1 means what? It becomes a linear point. R1 पनि same, यहाँ देखिए R1 पनि same, यहाँ देखिए S1 पनि same distance मा. If you plot the point, it's in the center. Even if R2 is equal to S2, so यहाँ देखिए R2 पनि same, यहाँ R2 यहाँ सारे S2 पनि same distance मा. So if you plot that graph, that's will be a center. So these points will come like a straight line. So when a transformation is having a linear straight line, we call it an identity transformation. We've done that in class. So there will be no change. So if R1 equals to S1 and S2 equals to S2, it's just an identity change. Now when R1 equals to R2, so say R1 is here, this point R1 is here, and this point R2 also is the same value here. So R1 and R2 is in the same line. So imagine the center line is not slanting, but the center line is straight. R1 and R2 is in the same position, right? And S1 is 0. So S1 is 0 means the center line is straight, and this point is not here, but this point is here. So it's coming like this. From here, it is coming straight. And S2 equals to L minus 1. So S2 becomes L minus 1. It goes right up. So the line becomes, from here it comes straight here, it goes straight up, and it goes straight right. So we've seen this somewhere. It's called a threshold function. We've seen this somewhere. So we've already done this thresholding enhancement. So when a piecewise enhancement takes up this values, these are special cases, it becomes identity. There becomes no change. When this piecewise takes up this values, this condition, it satisfies this condition, then it becomes a thresholding function. Thresholding function is a binary function where there is images are either black or white. Now the intermediate values are what we're interested in. Okay, so changing these intermediate values, left the values of R1 S1 and R2 S2, and we're playing around with it. We get different intensity values for different regions. So if you see this region, this particular graph, all values between 0 and R1 S1, okay, they are compressed, and all values between R1 S1 and R2 S2, they are not compressed, they are enhanced, they are brightened, they are spread more rapidly, they increase more rapidly. For every point in R1, there is a double fold in S1 S. So for every input value, the output value becomes more. Here, for every input value, the output value becomes less. For here again, it's compressed. For every input value, the output value becomes less. So in this piece and in this piece, this top piece and the down piece, the input values are compressed, bright values are brightened, and dark values are darkened, but the in-between piece, this is expanded. So we can play around with these values, and you can expand certain regions and you can not expand certain regions. Okay, now there are certain conditions that this takes up. So it has to be monotonically increasing and this and that. I think this the webinar has become too long and I don't want to prolong it any further. But the piecewise equation, the function looks something like this. Now all of these are equations of straight line, and the derivation, again, I would do it when we come back to class, because to type it and to find the equation was really difficult. I think I got another image processing. Okay, so so Nayan is, oops, so these are images from the Chatango, and I don't know why it pops up like this. The Chatango is really a very dirty script. Can you tell me, Nayan is asking me, can you tell me what is bimodal and trimodal in piecewise linear contrast stretch? Okay, so again, like I said, bimodal, trimodal, multimodal is not something to do with piecewise linear stretch. It is something to do with data distribution. So that is an assignment I think I gave you, because I cannot fully explain it here, but when your histogram has only one maximum value, okay, so this is an image which is a normal distributed image. It has a Gaussian distribution. It has only one mode. It has only one maximum value. But the moment your image takes up two maximum values, then this becomes bimodal, trimodal, multimodal. The modes keep increasing. The point that this histogram is making is there are 2 points in an image, 2 maximum points in an image around which a lot of values are concentrating. So there's a maximum point here, and a lot of values are concentrating around that point. There's another maximum value here, and a lot of other points are concentrating around this point. So this is what we mean by multi-mode. This is not one mode. So multi-mode को लागि धेरै आफ्नो आफ्नो टेक्निक्स हुन्छ हैन, सिंगल मोडको लागि धेरै धेरै आफ्नो टेक्निक्स हुन्छ, तर चलाउँदै नचलाउने होइन। मल्टिमोड टेक्निक, मल्टिमोड हिस्टोग्राम भएको डेटालाई अरु पाराले चलाउँदा पनि हुन्छ। It's not necessary. Okay, so all of these studies would come in univariate statistical descriptions of images. So that is something you've got to do. Okay, so this is the equation of piecewise linear stretch. So how do you get the output? So if, okay, so I'm getting another message here. Okay, so this is the piecewise linear stretch. Now, if x is between these ranges, then you can compute x is the input value, and x1 is the minimum, maximum, y1 is the maximum, x max, y max. Okay, so x1, y1 values you can see it from this image. Okay, x1 is r1, x2 is s1, x2 is r2, y2 is s2. So similarly, you can plug in the values, and you can have an equation set. So this is something derivation that we'll have to do it in class. I cannot do it here. But piecewise this is very important. Now you've got to look at this very carefully. Okay, now this is what I want to really show you. Now why piecewise also? So you piecewise piecewise theory that is, you get it everywhere. But how do you use piecewise and how it is really having an effect? It's something that we got to see, and this is what we're going to explain. Okay, Nayan says thank you. You're welcome. You're welcome. And this message is coming again and again. Please use the chat to ask questions regarding the webinar only, and let us maintain the politeness. That is something I've set from this settings. So it keeps repeating. I think you all you try and use this free platforms. Like I was saying, Rohit, the other day. And I'm a very big fan of open source softwares like QGIS is an open source. Now, there are a lot of open source softwares, free softwares that has been provided to us, and I think we are not using it properly. And I think this coronavirus lockdown has at least made me see that there are ways of using free platforms such as this. If in case any one of you want a video on how to do this entire setup and have a live webinar, you can write to me. We can do that someday. But if you want to research it on your own, you're most welcome. There are 3 or 4 things to do to set up, which I'll tell you at the end of this webinar. So coming back to the piecewise linear stretch. Now, why I'm saying is listen is this. Now derivation we'll do it in the class if it opens, but this is the equation. You've got to learn it somehow. How did you get the equation? This is we've got this true equation of straight lines, and I will do that in detail. So this is for the first case, this is for the second case, this is the third case. So these cases are here. X1 and Y1 will correlate to R1 and S1 in the above image, and Y2 and X2 will relate to R2 and S2 in the above image. Fine. Then these are 2 control points, X1, Y1, X2, Y2, and R1, S2, and R2. This is the image. Now how is contrast this piecewise image applied? So we've got this image. Now first let us understand this image. So because whenever you interpret images, whenever you want to be an image analyst, the first and foremost thing that one tries to find out is how well do you know the ground truths, how well do you know the ground points, how well do you know the area of study, or how well do you know the object of study, and based on that you plan your next steps. So I'm talking about classification, segmentations. So if you can see, this is a nighttime thermal infrared image. So thermal means the image is not a normal image. It is an image captured by sensors that captured heat, and this is nighttime. So of which area is of a Savannah River at South California, SC, South California, right? And Georgia border. So it's in the US, and contrast stretched means it has been enhanced. You cannot enhance it anymore. But from this image, I can clearly see there are 3 landforms, or at least 3 different images, 3 objects that I can identify clearly from this height. There is land masses. I can call this A. All these black land masses, yeah. And there is some kind of vegetation, but this is again landmass. Okay, and I can see a clear light gray, another object. Okay, and because we know this is a savanna river image, so obviously this would probably be an image. But if we didn't know it was an image, so it would be hard to really tell what is what. We wouldn't have said this is a landmass, but we know it's a savanna river image, so we know this is a landmass and this is a river. But had we not known, we would have said this is some object, some body, this is another body, and this is another body, this white is another body. So there are three distinct bodies. Since we are well aware of the ground truths, so this is the landmass, this is a river, and this is the what happened to my lights actually? Somebody switched off the lights. Oh yeah, I'm sorry. Okay, so this is the Savannah River. Now what this image is telling us is there are thermal plants somewhere here, hydrothermal plants, which produce electricity. So hydro power projects, and they've got this hot stream of some liquid, the water, the water with increased temperature that is being thrown into this river. So this white, because it's a thermal camera, it is captured that it is very high, whatever thermal, there's very high heat compared to the others. So the river, you can see it's uniform, it's the same temperature. The land has almost the same temperature here and there, because this is grass and some maybe rocks. But this has a very distinct temperature. This is very high. So from the thermal plants, or from the hydro plants, the water is coming that is a very high temperature and it is mixing with the river. And as it is going downstream, the temperature is decreasing and finally it is being diffused. A plume means like a smoke, so thermal plume. So somehow it is affecting the ecosystem of this river, because summers and winters, if you increase the natural temperature of a river, then all species are going to die. So this was a study there. Now, why is it important? So if you see the histogram of this, like I was saying, Nayan, that there are many objects. At least here I can see there are two distinct colors or two distinct objects. So here in this particular image, we've identified three distinct objects in a very large scale. If you go granular scale, there could be many other objects, but we got a very coarse, very far away scale. The far away scale tells us there are three objects. So tri-model. So that's the question. Nayan was asking me, so what is tri-model? So this, if you plot a histogram of this, there is one object here, one object here, and one object here, three different colors of an objects. So if you plot a histogram of this, here you go, almost a tri-model histogram. So there is A1, there is B, and there is C. So A is towards the darkest, 0 is the darker one, so towards the darker side of the images, A, and the chunk of the pixels are there. So this probably is the land masses here, okay, the darker side. And you've got the mid portion as the same uniform color. This very narrow band, so it's almost a uniform color, and there's lots of pixels. So uniform color is this is the only one that is uniform color, and a lot of pixels here. And then finally you've got bright colors, because 255 is brighter side. So compared to this, the brightest colors are here, and they've got high contrast. So some are bright, some are less bright. So this is very high contrast. This has almost no contrast. This is very narrow. So there's no contrast. It's almost same uniform. This is very high contrast. See, some are white, some are light gray, some are even lighter gray. So the area C of the histogram is pretty stretched in terms of contrast. The area of B is very narrow, so not very kind of contrast is very low, right? Now you say, sir, so we're talking piecewise. So now for example, we want to use the piecewise image enhancement just to enhance this plume, this thermal water, this white part. So we want to concentrate on this area. So all other enhancement would enhance the entire image. So piecewise is such a linear enhancement technique that lets us manipulate and choose which area we want to contrast stretch. depending upon the equation, this equation, fine. So we want to only stretch this part of the thermal plume. So how do you do that? So let's see. Now it is saying here, this river plume is composed of values ranging from 81 to 170, fine. It is ranging from 87 to 170. So the minimum value is 87, maximum value is 170, which can be seen in this statistics or some other statistics you can get. Okay, somewhere there. Then 87 to 76. We can use different piecewise contrast stretches shown in figure 7. Okay, so we know, so 87 to 170. So look here, 87 to 170. So we know that land is from 81. Okay, so the land value is from 81. So let's just see the logic. Here you go. Okay, so what he has found out is, I'm going to take my words back. So what he's found out is this section C, this area, this is the area that we want to see, the plume. These pixels are covering the region from this minimum of the C, you don't have to be exact. So the minimum of C is around 80 and the maximum that C goes to is around 170, 80 to 170, 81 to 170. So all the ones below are not, we are not very interested in. So what are we going to do using piecewise equation is, so we are interested in only 80 to 170. That's the plume. That's this plume, this white plume. Yeah, thermal plume that's mixing in the Savannah River. So what we're going to do is, here you go. We're going to take all values from 0. Here you go. Yeah. We're going to take all values from 0. This is the input value from 0 till where? Till 81. So here you go. So if this is a 0, the output is 255. If it is 1, 2, 3, 4, if it is 10, what is the output? 255. Whatever value it is here, till this line, you can see this dotted line is coming from here, it's coming till here. So all these values, all from here till here, all the values are converted to, where is it? 255. It was white. So all of this land and rivers become white. And all values from 80 to 170. So this is the plume. This plume. What is it? It is linearly stretched. You can see this line. So plume value. So if it's 190. So value 190 becomes what? Something in the output. Say 190. Then 80. Then you go maximum 180. So my 180 becomes something. So something. So all values are stretched. So only the plume area is stretched, shown by this line. Yeah. And all other areas are converted to 255. So you've got this beautiful image stretched, very nice contrast as compared to the other plume area. Here you go. This plume is not really very visually appeasing to see, but here we've done a piecewise linear contrast stretched, and we've got a very informative plume. You can also do this contrast stretch, piecewise contrast stretch to the entire image, not just to the river. Now you want to only see the river, not the thing. So all values below. So this peak is the river. So all values below the peak. The dotted lines are here. You go like this, and there is a contrast stretch here, and then it comes down here and goes here. So all values below this are 0, because this line is the line is here. it comes 0 0 0 0 0 0, and there's a steep line, the angle is very steep. So you're going to contrast stretch this entire river. Again there's a drop, see the drop, and again all C area value, all this plume area value again becomes 0 0 0 0 0. So all this is 0, all this is 0, only this area the graph is going, this is very steep angle here, and there's a drop. So this is a piecewise, one piece, two piece, and three piece suit. So there is a piecewise linear contrast stretch. So if you can see, you can visualize it. If you're able to visualize it, then it's easier to maintain. Now the next topic we got to discuss is these are the linear contrast enhancement. Now we've got the non-linear contrast enhancement. We've already seen what a log transformation is in the class. We've seen what the power law transformation is. Now the only one that we're left with is histogram equalization. Now, histogram equalization is a very important contrast enhancement, non-linear contrast enhancement technique, because it's very widely and commonly used. So what is the basis of this histogram equalization? As the name suggests, we require a histogram of an image, and taking the histogram of an image, we tend to equalize. So all of the histogram is going to be somewhat uniform. If there are certain peaks, we try and uniform all those peaks, and all of the histograms will have almost the same height kind of, and then stretch it, and we get a non-linear histogram equalization. Most of the image processing softwares will have this histogram equalization. Photoshops do have, QGIS do have. So we've already seen what a histogram is. So I will very quickly discuss this histogram, and this will be the last topic for today. I think we've already done quite a lot of video tutorial. So any questions so far? So if there's any questions, you can come up with the question, Nayan, since I know you're the only one there. So for the ones who are not there live for one reason or another, you can see this video. I'll have it till the next live does not come up. I really wish for the backbenchers, and especially the ones who keep sleeping, you know who I'm talking about, look at this video, because these are not very simple topics, and try and see them. So I think I will stop the video today, and we will continue the histogram equalization tomorrow or someday, and because it's coming up too long. And then now there are certain numericals we must perform, because it's a very interesting topic for contrast enhancement, this histogram equalization. So I was planning on finishing this today, but this seems a little too long. So what are we left with then? So let's come back. So we've done a min-max contrast stretch, we've done percentage contrast stretch, we've done standard deviation contrast stretch, and we've done a piecewise contrast stretch. Besides that, we've seen what contrast means. Besides that, we've seen what a histogram means. We've talked about what the image is, what the color image is, and we've done some background studies. In class, we've already done some non-linear contrast stretches like the log stretches. I don't know if we've done the power law, but we sure have done image negatives, identity transformations, and today we've also done the thresholding. So we've done thresholding, min-max, percentage, standard, and piecewise. So in the next class, I will, which I actually had intended to do it today, but next class we'll do the histogram equalization. And there is another one where I have not written is gray level slicing. So we'll do what is histogram equalization, how is it used, we'll do some numericals. Then again, the derivation is, we're not going to do it here because it's very difficult for me to really find the characters and type in. Then we'll come to neighborhood processing. So far we were mostly doing point processing. Now we're going to do neighborhood processing. So neighborhood processing is also called filtering or masking. And again, here we can categorize them in two ways. One is a linear way, linear neighborhood processing or spatial filtering, or non-linear filtering. Or you can group them as smoothing, low pass filters, or sharpening, high pass filters. So this is any way you can categorize them. But remember, all of this all belong to spatial enhancement technique. We've still not gone to